go then. All right, so yesterday we had kind of completed all of this. We talked about the average velocity. We talked about velocity. Unfortunately, I erased the board, so really quickly I'm going to recalculate my Vx. So just as a quick reminder, the velocity in the x direction is just the derivative of the position. So that turns out to be what? Negative 4.5 OT squared plus 12.0 T minus 4.5 O. And then our velocity in the y direction is the derivative of y with respect to t, which is what? 6.00 t squared minus 24.0 t plus 16.0. Okay, so is everybody good with that from yesterday? All right, and then to find the velocity at one instant, you just plug in your time, and you can either write it in unit vector notation, right? So it would be this guy I plus this guy j. Or you can write it out, do the Pythagorean theorem and find your magnitude and your angle. Cool? All right, so that was that. Now, today what we need to talk about is finding average acceleration. It's the same thing. So we just talked about how to find average velocity and instantaneous velocity by looking at the position, right? So now we're going to do average velocity and instantaneous acceleration by looking at the velocity. Okay? So your average acceleration is exactly what you guys learned it is. Like last year, ideally, you guys learned A average is Vf minus Vi over T, right? Well, same thing, except that now our velocities, instead of just being, one-dimensional, they're vectors. So there's, an x and a y component. But, you just subtract your two vectors and divide it by the time it took. So you're going to take your change in velocity and divide it by the time it took. And then if you want to find your instantaneous acceleration, then you take the derivative of your velocity with respect to time. All right, and just like we did yesterday, we had x and y components. Same idea. Our acceleration is going to be, in 2 or 3 dimensions. And so you're going to need to take the derivative of the x component, take the derivative of the y component, and if there is one, take the derivative of the z component. Exactly like we did yesterday. Follow? Yeah. You sure?
Okay, well this might seem like a stupid question.
Not at
all. Isn't horizontal velocity always constant?
Oh, I gotcha. For a projectile, that's true. So like, yeah, if you, throw a ball up in the air, horizontally there's no forces acting on it. So, yes, in the case of a projectile, yeah, the horizontal velocity is constant. But yeah, these don't necessarily have to be a projectile. And furthermore, in the real world, even projectiles aren't projectiles because there's air resistance, right? So in the real world, your horizontal velocity for a projectile isn't even constant. So, everybody good? All right. And I think we'll learn how to deal with air resistance. I think it's chapter 5, it might be chapter 6, but it's coming up. Okay. So basically today is going to be kind of more of what we did yesterday, but instead of talking about how quickly the position is changing with respect to time, we're talking about how quickly the velocity is changing with respect to time. All right? See you later, Patrick. Good luck. All right, so our acceleration is a vector. There's a horizontal acceleration, a vertical acceleration, and a out-of-the-page acceleration, x, y, and z, right? So just like we did yesterday, there's a horizontal, it's the derivative of the vx, vertical is the derivative of the vy, and then the out of the page is the derivative of the vz. Cool? All right. So again, I really think the best way to do this is just by doing some calculations. So a quick comment here. Oh, no, that's not. I can't imagine anybody getting tangled up about that. I think opening that can of worms will be more confusing than leaving it. All right. So let's take a look at this. It says there are 4. This is again one of those book examples, and then we'll go back to the drone example. All right. So the book example is this. It says here are 4 descriptions of the position in meters of a puck, so presumably a hockey puck, as it moves in an XY plane. So there's 1, 2, 3, 4 different ways of describing it. And then it says, are the x and y acceleration components constant? Thoughts about how we would find that? let's do number 1. So number 1 gives us this. It tells us that our position at any given time is negative 3t squared plus 4t minus 2. And our vertical position is 6t squared minus 4t, right? Cool. So could I find my velocity at any given instant? What would we do? Just take your derivatives, right? So my horizontal velocity would be the derivative of x with respect to t, and take your derivative. So you get negative 6t plus 4, right? And my vy would be my derivative of y with respect to t, which is going to give me what? 12t minus 4, right? Good? So those are my velocities. Now what do? Now you find your accelerations, right? So my acceleration in the x direction is the derivative of vx with respect to t. Oops, dt. So that's going to give you negative 6, right? So that's constant, right? No matter what time is, that's my horizontal acceleration. So that is a constant horizontal acceleration. And my ay would be the derivative of vy with respect to t. So that's just 12, right? So again, constant. So example 1 has constant acceleration in both x and y directions. Follow? Now, does anybody see a shortcut way that we could figure this out without actually taking a derivative? What do you got, Nikki?
Power over 2, and it's not constant.
Good, yeah. So my position depended on time, right? It depended on the highest power was t squared, right? So when you take your first derivative, that's going to drop you down to t. And when you take your next derivative, it gets rid of the t altogether. So it's constant, right? So take a look at example number 2. I don't know if you guys can read it. Oh, you have it right in front of you. It's negative 3t cubed. So when I take my first derivative, it's going to drop down to t squared. Follow? When I take the next derivative, it's going to drop down to t. So that means my acceleration there depends on t. So my acceleration here is going to be something times t. Not constant, right? Because it depends on the time. Does that make sense? All right. Now, 3 and 4, they look a little more intimidating because, like, for 1 and 2, I gave you expressions for the x position and the y position, right? In 3 and 4, I didn't do that. I gave you this r. Did I just hear somebody say it's the same thing? Isn't it the same thing? Right? Because look. This says r equals 2t squared I. So 2t squared is my x. Right? And then my j component is 4t plus 3. That's my y. So my x position is 2t squared, and my y position is 4t plus 3. So when I take my derivatives, am I going to get something constant or not constant? Constant, right? Make sense or no?
Just for the y, should it be like a negative 4t minus 3? Because
You're 100% right. Yeah, there's a negative sign in front of that, so I should, yeah, for sure. Thank you. But it's still, when you take your derivative, it's still going to drop out. But you're totally right. I should have been more careful about that. Okay, and then your third one, we got a 4t cubed. So that one, when you take your derivatives, you're still going to have a t term. Cool? All right. Did I do any of that too fast? Everybody's good? Yeah, good.
So I understand the x and y acceleration being constant or not. What's the second half of the question? X is acceleration.
So this is our acceleration in the x direction. This is our acceleration in the y direction. How would you find the overall acceleration? Pythagorean, right? So yeah, I mean, if both of your components are constant, then certainly your overall will be constant, right? But if one of your components isn't constant, then the overall will be constant. Does that make sense? Christian? No. Yeah.
Example, the resultant vector one, so 3 or 4, can you just spell it out?
Say that again? Oh, yeah, sure. Gotcha. Can I erase what's here in red? You got a preference? Why don't we do 4, since the acceleration there isn't constant? All right, so for 4, here's what we've got. I know that my position at time t is 4t cubed minus 2t, that's my I component, plus 3j So my velocity at time t, so there's a couple ways you can do it. You can literally divide it up into, make this your x and make this your y, and do exactly what I did with number 1. If you want, you can kind of just do it at once. I want the derivative of r with respect to t. So I'm going to take the derivative of this, and I'm going to take the derivative of that. So the derivative of this thing is going to be, let's see, 12t squared, right, minus 2. That's my I component. Plus, what's the derivative of 3? 0. So it looks like this thing is only moving horizontally, right? There is no vertical motion. Does that make sense? Because my j component is 0. Follow? All right, so now I can find my acceleration at time t by taking the derivative of v with respect to t. So I'm just going to take the derivative again. Oh, shoot. I forgot my squared here, didn't I? I'm sorry. Make sure you have that squared there. Okay, so my equal sign is ugly. All right, so take your derivative again. So I'm going to get 24t minus 0. So that's my I term. And then j is still 0. Cool. So what this is telling me is that my overall acceleration is only in the horizontal direction. The acceleration depends on the time. And it's equal to 24 times however much time has passed. Cool. You good, Christian? Everybody good? Awesome. All right. All right, so let's go back to the drone example. It asks you to find the acceleration after 2 seconds. So if I had been smart, I would have, oops, too far. Copy. Paste. Okay, so those are the velocities that we figured out yesterday and then again very quickly at the beginning of the hour. So to find the acceleration, all I'm going to do is differentiate each of those things, right? So my horizontal acceleration is going to be just the derivative of this mess, right? So that's going to give me negative 9.00 t plus 12.0. And my vertical is going to be the derivative of this guy, which is 12t minus 24. Cool. No? So it says find the acceleration after 2 seconds. So, option 1. Wish I'd given more room, I'm sorry. I will leave more room in the future. Let's do it in unit vector notation. All I'm going to do is I'm going to plug 2 in for each of these times. Okay? So AX after 2 seconds is, let's see, negative 9 times 2 is negative 18. Plus 12, you get negative 6. Did I do that too quick? Yep. Yeah, tell me if I'm going too quick, you guys. Also, just so you guys know, I'm hoping my notes will start to get better too. I'm almost done with all of the problems in Chapter 4, which means that I will finally be more than a chapter ahead of you. So hopefully I should be able to make my notes a little bit more. All right, everybody good? Okay, so that's my horizontal acceleration. It's negative 6. Similarly, I can find my vertical acceleration after 2 seconds by just plugging in 2. So, oh shoot, we get 0 again. I really wish I'd picked a different time. Would it be horrible if I just changed my time to 3 seconds? Is that okay? Does anybody mind? Because I know that was confusing yesterday. You guys were like, well, what would happen if it wasn't a 0? So let's do what happens if it's not a 0. So before I do it, let me make sure that 3 doesn't give a 0. Okay, so let's pretend that this had said 3, and it also shouldn't say seconds while we're at it. It should say hours, right? Okay, so that's going to change my AX. I apologize. I should have known better. I always try to avoid having zeros in my examples. You'd think that... Okay, so after 3 hours and after 3 hours. So let's see, A after 3 hours, so we're going to have negative 9 times 3 is negative 27, plus 12 gives us what, negative 15 now? And presumably our units are going to be what, miles per hour squared. So miles per hour squared. All right, and then AY after 3 seconds, 12 times 3 is 36, minus 24 gives us 12 miles per hour squared. Everybody good? All right. So then I would write, okay, well then my acceleration is, here, I ran out of room. So my acceleration then is negative 15I plus 12J miles per hour squared. Or if you wanted, you could write it in magnitude and angle form. So I would do the Pythagorean theorem, which is going to give you whatever, 18 or 19, whatever it turns out to be. Would be bigger than that, but whatever. And then find your angle, right? So let's do that real quick. Yeah.
Does that acceleration go with vector sign over, or is it?
Yeah, totally it does.
But I wasn't trying to be picky.
No, you're good, you're good. And you guys police me on that, because I'm really bad about my vector lines. All right, we're good? Okay, so now I can do option 2, which is magnitude and direction. So basically what I'm going to do is I'm going to say, all right, well, I know that I've got a horizontal component of negative 15 and a vertical component, horizontal component of negative 15 and a vertical component of 12. So I can find my A by just doing the Pythagorean theorem, right? So almost a 3, 4, 5 triangle, but not quite. It's a 3, 5 something triangle. All right, so square root, try again. Square root of 12 squared plus 15 squared is, so you get 19.2. So 19, we got 3 significant digits, so we can stick with that. Miles per hour squared at, and remember, when you find your angle, you guys, you always find the angle, wherever you started your drawing. So I'm going to do inverse tangent of 12 over 15. And it gives you 38.7 degrees. And then how would I describe that?
North of west.
North of west, right? Everybody good with that? Problems? Okay, cool. So then the last thing we got to do is find the average acceleration. So if everybody's good, I'll erase all this and we'll do the average acceleration. Yeah, what do you got, Ethan? Yep. Or you could just leave it. So either of these two answers would be acceptable, depending on, sort of the form you wanted to give. You could give it in unit vector notation. Or if you wanted magnitude and direction, then yeah, this would be your full answer. Cool. And like I said yesterday, unless I say otherwise, I want this. If I want this, I'll ask for unit vector. Cool. All right. Very good. We are almost done then. So can I erase or? One once. Everybody's good? All right. This whole duck thing is funny. I did the same thing to my parents with pigs once. No, they were about the same size. They were these little pigs that I bought. They were, for some reason, they were at Rite Aid. They were like 5 cents each, and they had this giant crate of them. And I was like, I'll take them. So I bought like 200 of these things. I don't know. I gave them. put them around my parents' house, and then they, I don't know, they had some party and they had people decorate it. I don't know what happened, but they're gone now, and I'm sad. Okay, so let's do this. Let's find the average acceleration in the first. We'll stick with 3 seconds again, and again, I guess, hours. Okay, so to me, finding the average acceleration is a little bit easier, but you just got to be careful and make sure that you remember what you're looking for. So the definition of average acceleration is, I mean, it's VF minus VI over T, right? I mean, that's, very honors physics-y and not AP physics-y, but that's what we want to do. So we want to find the velocity at the end of 3 hours, the velocity at the start of those 3 hours at time 0, and then divide by the time, which is 3, right? So there's our two expressions for velocity, right? So let's do this. Let's find our velocity at time 0. Let's see, Vx at time 0 is negative 4.50 I plus 16.0 J. And I guess I shouldn't have put the X there, since that's actually our overall velocity, isn't it? How come it's plus? Because it's plus 16. So if your T's are 0. Are you good? Is everybody good? So all I did there is I put in a time of 0, and I found my velocity at a time of 0. That's going to serve as my initial velocity. Good? All right, now let's find our final velocity. What do I do? Plug in 3 for my time. So my velocity after 3 hours is going to be, well, let's see, 3 squared is 9 times 4.5. I'm going to grab a calculator because I am. So 9 times 4.5. Why don't I do the whole thing at once? So I'm just putting in 3 for this. So plus 36 minus 4.5. So I got negative 9. Yeah, Marcus?
Are we going to do this chapter like dealing with X, Y, and Z?
It does happen from time to time, yeah. But it's just one more component to keep track of. So it's not sort of harder, it's just more tedious and annoying. All right. Plus, all right, now I got to put in 3 for my time here. So let's see, 9 times 6 is 54, minus 72, so that's what, negative 18. Plus 16, you get negative 2. Did anybody do that with a calculator? Oops, is that right? Did I do something right for a change? Is that good? Okay, yay, me. All right, so now what do? Subtract, right? Final minus initial, right? Oh, you guys okay?
Yeah.
You can talk to me, what's going on?
So you plug in 3 for V of X and push the button up.
That's my I spot. You good? Everybody good? Ask if you got questions, you guys. I promise if you have a question, you are not the only one. How many other people were confused about that? Liars. Oh. Correct. Yeah. Yeah, so this is the I. This negative 9 came from putting 3 into the Vx equation. And the negative 2 came from putting 3 into the Vy equation. Good? Because this is the X component of our velocity, and this is the Y component of our velocity. Yeah.
Will we end up having a unit vector notation like vector as our answer?
Again, you can write it either way.
Well, for this.
For this one, I mean, technically I didn't ask for it in unit vector notation, so we'll have to convert it.
But you just subtract the 2 and then divide by 3.
Right.
Have something high. Something great.
Yep. All right, is everybody good so far? Matt, you good? What's up? You sure?
Yeah.
Mickey?
Yeah, I'm good.
You're okay. That wasn't me yelling at you for talking. That was me making sure you were good. All right, so that's that. So now that means that VF minus VI, let's see. So VF is negative 9 minus negative 4.5. So that's going to give me negative 4.5, unfortunately. It's an unfortunate coincidence. And then here, let's see, negative 2 minus 16 gives me minus 18. J. Did I do that too quick? I just did my VF minus my VI. So VF minus VI. And then I'm going to divide it by my time, which is 3 hours. Cool? And you can just divide component-wise. So negative 4.5 divided by 3, this is what I forgot to do on the homework. So negative 4.5 divided by 3 gives you negative 1.50 times I. Because negative 2 minus 16. Remember, you got to do final minus initial. No. Yeah. So yeah, make sure you do final minus initial, not the other way around. All right, and then negative 18 divided by 3 gives us negative 6. So there's my average acceleration. What should the units be? Miles per hour squared. Cool. All right, so now our last thing is, so that's unit vector notation, and then you could convert it into magnitude and direction, which you guys know how to do. Cool? Yep. Yeah. Again, if it doesn't say, assume that I want it in magnitude and direction. Cool? And I'll be honest, you guys, well, maybe I shouldn't say that. My thinking is probably after this chapter, if it's easier to leave it in unit vector notation, you can leave it that way. But this chapter, I need to know that you're comfortable, going back and forth. All right, are we good? All right. All right. Here's an example. One last example. So it says, suppose a bird with a jetpack is flying at a velocity of 5I minus 2j meters a second at the instant he switches on the jetpack. Okay? It says x, y are north and south. Wait a minute. X? How does that work? I have no idea what I was trying to say there. Yeah, I was just going for north, south, east, west, and I wrote it crappily. So x is east, west, north is, or y is north, south. You know what I was trying to say, or hopefully you do. All right. All right, so it says, unfortunately, the jetpack is on crooked. So it gives him a constant acceleration, but at this weird angle. All right? Find the bird's instantaneous and average velocity at the end of 5 seconds. Okay, so what does the 5I minus 2j represent? More specific. Yes, it's velocity. V0. That's the velocity at time 0, right? So our velocity, with an arrow over the top, at time 0 is 5.00I minus 2.00j. And those are all in meters per second, right? Now, this 4 meters a second squared at 30 degrees west of north is my acceleration, but it's in magnitude direction form, right? So what do I probably want to do? I don't know why I made that request. Split it up into the components, right? So let's do that. So let's see. We want west of north. So here's north, here's west. Here's my vector. Where's the 30 degrees? Is it above or below? Above, because it's west of north, not north of west. So here's my A. I need to find AY and AX. Is everybody okay with why I put my arrows on AY and AX pointing the way I did? AY is north because we're accelerating north. AX is west because we're accelerating west. Northwest, right? Cool. So AX is going to end up being 4 times the sine of 30, which is just 2. And AY is 4 times the cosine of 30, which gives you whatever 2 times the cosine of 30 is. Please notice, Alex is about to ask something.
Since it's going west, is it negative?
Yes, thank you. Yeah, 100%. I was going to put my negatives on at the end. What I was going to say, I was thinking of something else. Notice the horizontal component is not always cosine, right? Because it depends on which angle you're using, right? A lot of times I see people do that. They'll just go, oh, horizontal, use cosine. Vertical, find sine. Ugh, you got to be careful. It depends on the angle you're given. Okay? All right, so let's check this out. 4 cosine 30 gives you 3.46 and then some other numbers, which I should write down, but in the interest of time, I'm just going to round off like that. All right, and then finally, remember, the calculator won't tell you your signs, your positives and negatives. And so like Alex said, you got to look at your drawing and go, wait a minute, AX is pointing in a negative direction, so it's going to be negative style. Cool. All right. So, can I shrink all this? Everybody got all this? Boop, 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 boop. All right, so I'm going to put this over here. All right, so what we just figured out then is this. Our acceleration is negative 2.00I plus 3.46J meters per second squared. So what this is telling me is that this is telling me my horizontal acceleration. This is telling me my vertical acceleration. So thoughts about what I'm going to do?
I have a question.
Oh, yeah, shoot.
Should we like round it off like that, or should we just leave it like 2 or 3?
Yeah, I would. Yeah, and I mumbled that, I think. But yeah, you want to keep some extra significant digits until the end. Okay? And I'll be honest, I think what the book does is the book leaves it as 4 cosine 30 and just keeps 4 cosine 30 until the very end. So, yeah. Okay, yes. So why are we multiplying A by 5? Yeah. Oh, I see what you're doing. Yeah, yes. So remember, you guys, the acceleration tells us how much the velocity changes every second, right? So remember this equation? So we're going to use that equation. Look, we've got constant horizontal and vertical acceleration, right? So you can either think of it as a horizontal thing, so VI would be 5, acceleration is negative 2, and time is 5, and that'll give you your final horizontal velocity. And then repeat the process for your y, or just do it all at once. I'm going to just use this equation. I've got constant acceleration. They happen to be vectors, but it's still a valid equation. Does that make sense? So that means my VF here is going to be, let's see, my initial velocity was this, 5.00I minus 2.00J, plus my acceleration is this mess, negative 2.00I, damn it, plus sorry, I'm just trying to figure out how to fit it all on the board. VF equals, there we go. So my A is 3.46J times my time of 5 seconds, which is what Ethan just said a second ago. Multiply your acceleration by your time, right? Follow?
Yeah.
This. Oops. I never know which is better, having it like super huge like this. I wish there was like a happy medium, but it's kind of like all or nothing here. Okay, so now I'm going to deal with my I components and then my j components. So I'm looking at 5 minus 2 times 5, right? Did I lose you there? Mickey?
No, I got it.
You sure?
Yeah.
Just grouping your I components. So it's this minus this. So we're going to get, so 5.00I minus, oops, minus 2.00 times 5.00. So that's my I, all kind of grouped together, right? I don't know that you have to write this step out, but I'm just showing you what I'm doing. And then repeat the process for your J. So plus negative 2.00 is my starting y velocity, plus 3.46 times 5.00 J. Follow or no? Kurt, you good? Everybody good?
Yeah.
Okay, cool. So let's simplify it. So 5 minus 10 is going to give me negative 5.00 I. And then over here, 5 times 3.46 is, what, 17.3? Minus 2 is 15.3. And then what are my units going to be? Meters per second, because that was a velocity, right? Yeah.
So is it just, like, why isn't it 5 minus 2 and that times the 5 seconds?
Because the equation says take your initial velocity,
Oh, and then
and then you're adding, so this quantity here is your change in velocity. You're accelerating at this rate for this many seconds. So this is how much your velocity is going to change. And so then all I sort of did was I said, all right, well, this is what's going on in the x direction. This is what's going on in the y direction. Alex and then Matt.
So should we be like remembering all those kinematics equations right about now?
Yeah. Guns. Yeah, Matt.
This is too late, but
You sure? You got a question. You're not the only one. Okay. Come around it. Cool. Okay. Everybody good? All right. Okay. Was that the only thing we needed to find? I don't remember now what we were trying to do. Let's see. Oh, find the average velocity. Okay. Oh, yuck. Okay. So finding the average velocity is a little bit harder. Oh, you know what? I'm lying. It's not bad. So here's why I was thinking it was bad. So the definition of average velocity is change in position over time, right? Okay. So I'd have to find my starting position, which I guess you would assume is 0. Find your final position by using 1/2 AT squared plus VIT on each of those vectors, which you could do. It would be, some work, but you could do it. And then, do final position minus 0 divided by your time. But there's a super secret ninja shortcut we can take. You know it, Alex, or do you got a question?
nope.
What was your question? All right. Okay, does anybody see the super secret ninja shortcut? We got it?
That's kind of what like, is it just Vm minus Vi over?
That's the acceleration equation. You're in the neighborhood, though. We've learned 2 equations for average velocity. So there's the definition, which for us, this chapter really is this.
The interval of the acceleration.
Easier than that. You guys remember that? So that's an equation that you can use if acceleration is constant. Is our acceleration constant?
Yes.
Let's see, I think it was. Our acceleration is a constant 4, right? So, I just found my final velocity. I know my initial velocity, so I can literally just average them. Make sense? All right. Or you could go about it the long way, find your displacement, using the 1/2 AT squared equation. That would work too. All right. So, I wonder which way I did it in my notes. Yeah, I did it this way. Real quick, I guess I should check and make sure that this answer I have in my notes is the same as what I just told you guys. Make sure I didn't make a mistake somewhere. -5 minus 15 plus. Oh, this was supposed to be plus. My bad. I missed a neg. All right. I said it right, but I wrote it wrong. It's 15.3 J at the end of our velocity should have been plus. Glad I checked. Okay, so almost done. In our last couple minutes, we can finish this up. So we're going to use this average velocity equation. So V average equals VF plus VI over 2. So we just found our VF. It was negative 5I plus 15.3J. And our VI was given to us in the problem, wasn't it? It was 5I minus 2J. Right? Add them up and divide by 2. So negative 5I plus 5I is going to give me 0I. And then 15.3J minus 2J is going to give me 13.3J all over 2. Which gives you what? 6.75? 6.66? 6.65, thank you. J, and then my units there are meters per second. Cool? All right, so long story short, you guys, really what we're doing is we're just keeping track of, instead of just worrying about the motion in one dimension, we're worrying about motion in 2 or sometimes 3 dimensions, and just keeping them separate by marking them with either an I or a J. All right? Cool? Okay. Cool. So the second chunk of that assignment will be due, what is it? Monday, right? Yes, and then yes. So that wasn't enough. Yeah, but yes.
So we're told to write the magnitude direction. So it would be 6.65, but just north.
Exactly. Kelly just asked a really, really good question. Let's make sure you guys get this. So this is in unit vector notation. How would I write this in magnitude angle notation? The magnitude would be 6.65 meters a second. And what's the direction? Not 0. Let's see what was going on. North, because our y plane was north-south, right? Make sense?
Yeah.
Your j component would be north.
Do you want it in like north, south, east, west, or
Say that again.
can we just put polars or
You should make sure that your answer relates to the question being asked. So if the question is about north, south, east, west, your answer should be north, south, east, west. If it's talking about pushing a lawnmower, then you might say so many degrees above or below the horizontal. You know what I mean? Make sense? Vicky.
Would there be any application?
Say it again.
Would there be any application to multiplying two vectors together, not dots or cross?
That question doesn't make sense. Like, and I don't mean that in a mean way. Like, if you're multiplying two vectors, you're either doing a cross product or dot product.
That's what I told.
Like that's all it is. Okay, well then you were right. So Jack. All right. Does that make sense?
Yes.
Okay. So, and we'll see applications of both of those as we go through the year. All right. Again, if you're struggling, I'm around before and after school. I'm more than happy to help. Yeah. Yeah. Come on. Oh, are you sure? Can I ask what you were going to ask?
Like I get that, but
You're grouping all the eyes. So really, yeah. Yeah, we got a lecture either tomorrow or Monday. Probably one or two problems tomorrow and then lecture Six eight. Oh, okay. So you're trying to find average velocity. I'll look at what we got here. Oh, I see what you did. Okay, so when you do, oh wait. Oh, 2 seconds. So this is your time, right? So this is like your xf minus your xi, is that what you did? Okay, you can't use magnitude. You can't just subtract the magnitudes. You've got to do them component wise. So what you're going to do is you've got two positions, right? Starting position, which is 0. Yep. And then you've got an ending position, you plug in 2, which is ending this, right? Oh no, that's the velocity. Yeah, so you plug in 2. Yeah. So plug in 0 for t, plug in 2 for t, so that'll give you a final position and an initial. Subtract those. And then you subtract them component wise. So you're going to do I minus I, j minus j, k minus k, and then final that back to 2. Does that make sense? And that's just because that's how you subtract vectors. You can't sort of subtract just magnitudes. You got to take into consideration.
Right.
That's,
Yeah, when are we gonna get the test back? Like this, yeah, one where like which picture shows the subtraction.
yeah. So yeah, I'll show you guys a super secret in the way to do it. And I think I showed a couple people, Mary and Elizabeth are both in my tutorial. I showed them in your tutorial, and they're like, oh.
Okay.
So it was something that I thought you guys knew, but it seems not. And like I said, I get it. Next year I'm going to start at ground zero.
Yeah, that's what we do in most of the classes.
Okay. Yep. And like I said, this is my first year, so I appreciate you guys being patient. And if that test is the one that breaks your grade, then we'll figure something out. So don't stress.
Thank you.
Yeah. Thank you. See you later. Okay. She asked me this morning if she could come in and get some help. So do you mind if I help her real quick? Thank you. All right. Thank you, Kelly.
Yeah, no problem.
Okay, so are you good with this velocity time graph?
Yeah.
So, so your position time graph looks okay too.
Oh.
Is this what you did in class and you just don't understand it?
Oh no, I get, because we did this one in class, but like this one, and this one's all wrong.
I gotcha. Okay. Well, this one is literally the same as this, except you make everything that's positive, you just make negative.
Okay.
You know what I mean? So it kind of doesn't, I mean, if you think you understand this, our time is probably not best spent going over this one, because it's kind of the same thing.
Okay.
But just your position starts at 0 and then becomes negative. And your velocity starts at 0 and then becomes negative.
Okay.
Cool? So, but this one is definitely one you should know how to do. And this one. Okay, so let's see what you got. All of this is perfect. Do you understand all of this?
Yeah, I get that stuff, but I just don't use how to get this.
How to get these guys?
Mhm.
Okay. So, so let's worry about this in a second. So you're good with the velocity graph?
I think so. I wasn't sure if it was right or not.
Yeah, because your velocity is going from 8, and then it says it takes 10 seconds to slow down to 2. So this whole time you're slowing down, and at the end of 10 seconds, your velocity is 2. And at 10 seconds, your velocity is 2. Cool. Now, you found your acceleration is negative 0.6. So your acceleration should be negative 0.6, just a horizontal line at negative 0.6. Does that make sense? Okay. Cool. All right, so finally this guy. So it doesn't tell you what the initial position is, and I told you guys in class that if it doesn't give you one, it doesn't give you a starting position, then just assume it's 0. Okay? So here you made your final position 0, which, I mean, I guess you could, but I asked you guys to make your starting position 0. It doesn't really matter. So all that's, okay. And the numbers you had made sense, it just was, sort of like shifting. All right, so if our starting position is 0 and our displacement is 50, what's our final position? So you're starting at 0 and then going forward 50, right? So on your position graph over here, you can kind of do exactly what you did, except instead of calling this negative 50, let's call it 0, and then just go 10, 20, 30, 40, 50. See?
Oh, so this
So your
is
graph
no
actually,
negative.
not in this one, correct? Because you're starting at a position of 0, and then you're always moving forward. Now, it wouldn't be wrong to, put 0 across the middle and then just count up from there. You just wouldn't be using the bottom half of your graph. And what you just erased was totally fine. Okay? Because at time 0, your position is 0, so you're going to have a dot there, right? And then at the end of 10 seconds, your position is 50. Right? And then, so you got to connect the dots. So then the question becomes, is it a straight line, is it a swoopy line, or a swooshy line? So,
Well, because it's increasing.
when you say it, what's the it? In this case,
I can't remember if it was this one or this one. I think it's this one.
it's the velocity. It's how fast you're going. So you want to look at these numbers. Yep. So at the beginning, you're going very fast, which indicates steep, right? And then you slow down, which means it's going to get less steep. So what you had was perfect. You started out steep and then got progressively less steep. All right, are you all set, Daniel?
Yeah. Only thing is, I just remembered. Yeah, my calculator is like no battery.
Oh, I gotcha. So we have a couple options. One, I can loan you one. Option 2, I can loan you one. I'm not sure if I have an option.
Can you get my shoe scheme?
Sorry?
The shoe scheme, remember that?
Shoe scheme.
Buy cheap shoes, trade up your
Oh, I gotcha. Oh, yes, I gotcha. You don't need to do number 7. It doesn't make sense. I'm going to put the cap on the floor. You can use this exactly like a graphic calculator. You know what I mean? Like, you just type it in. It's literally the same thing. Instead of, you're going to use second sine or second tan or second cosine to do inverse. Cool. Other than that, I think it's all the same. Cool. Let me know if you need anything clarified. Does this make sense?
Yes.
Okay. So, what was it that was messing you up before? Like, because you walked in the door and pretty much everything you had was fine, except you had your starting positions a little funky.
Oh,
But that might have just been.
I thought I did everything right.
Okay. No, I mean these all look good. This looks good too to me.
I think I did this one for sure wrong because
This one, yeah, it's close, but it's not perfect.
okay. I erased.
Well, let's not erase anything. Let's leave what we got so far. So your initial velocity is 12. It's not going fast enough, so it accelerates at -3. You think of the F, -12. Your time is 8. Love it. Your velocity graph looks good. You found your displacement and got 0, which, good, you're supposed to get 0. Okay? So again, let's assume our starting position is 0. And if your displacement is 0, what's your final position going to be?
0.
Also 0. So what we just learned is that over here on our position time graph, at the beginning our position is 0, and at the end our position is 0. Okay?
Now we have to find the 4.
There you go. There you go.
Okay, so
Okay.
then I do the displacement equals 1/2.
It works.
Oh, 12 plus the negative.
Oh, I see what you're doing. Okay, so you're doing the screwdriver. 1/2 VF plus VI times T, right? So what are you trying to find right now? I feel like you're diving in without writing out your given information. So you're about to work in a circle. You're doing the same thing you just did a minute ago.
I meant to do. I'm trying to find the
Displacement
yes,
from where to where? Show me on your drawing.
from here to here and then like down. Or well, this point.
Yeah, at that point from the start, right? So show me on your velocity time graph. You're trying to find the displacement from where to where. That's your end point, where's your starting point. If you start there at time 0, and you want to know what the displacement is after 4 seconds, because that's where the velocity is 0. So, what's your VI?
0. Of,
Let's do this. I feel like you're...
12.
Yes, but here, let's make sure I understand why. So here's what's happening. So there's a ramp, right? So this, the idea is we've got an object that's rolling up a hill. The beginning of the problem is going up very quickly, 12 meters a second. Then as it goes up, it slows down, slows down, slows down, and after 4 seconds it stops, and then it comes down the hill faster, 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 right? We're trying to find the displacement from here to here. From here to here. So,
Oh, so this would be your initial 12, 0 would be your final, and then 4 seconds.
there you go.
Okay.
Does that make sense? Because all we want to know is how far did it go during the 4 seconds it took to stop. Cool? So your starting position 0, ending position 0, we got to find the one after 4 seconds.
Okay, so
Cool.
then you use the
So now you can use your screwdriver, but you just got to make sure you put in the right guys.
displacement equals.
Oh shoot, I'm still recording.
Okay.
I did the same thing last hour.